In this video, we're going to take a look at strategies for solving systems of nonlinear equations. By a system of nonlinear equations, we simply mean a system where at least one of the equations is nonlinear. It is possible for such a system to have a linear equation, but the key is that there is at least one equation which is not linear. We begin by recalling the two basic strategies for solving systems of linear equations. That would be substitution, where one of the equations is solved for one of the variables, and then that expression is substituted into the second equation. And elimination, where we multiply one or both of the equations by non-zero constants and add them together to eliminate one of the variables. Both of these strategies for solving linear systems can be extended in sort of an obvious way to solve nonlinear systems. However, unlike with most linear systems where substitution and elimination can be used on almost any problem, there are certain systems where only one of the two approaches will efficiently give us a solution. And so we do need to be comfortable with both substitution and elimination, and often have to decide which approach to use before we actually go and solve the particular system that we have. For our first example, let's consider the system of equations x minus y equals -1 and y equals x squared plus 1. Notice that this is a system of nonlinear equations. Even though the first equation, x minus y equals -1, is linear, the second equation, y equals x squared plus 1, is not linear because it contains an x squared term. And since at least one of these equations is nonlinear, this is a nonlinear system. In order to solve this system, one approach would be to use substitution by solving for one of the variables in the linear equation and substituting it into the nonlinear one. For example, here we could solve the first equation for x, and this would involve adding y to the other side, and so we obtain x equals y minus 1. Right. We can then substitute this in to x into the second equation, which would yield y equals y minus 1 quantity squared plus 1. We'll now use algebra to simplify all of this out. And so we're going to have y equals y squared minus 2y plus 1. Remember, we do need to expand the y minus 1 squared completely to get y squared minus 2y plus 1. We can rearrange this. This will be 0 equals y squared minus 3y plus 2. And now this expression on the right-hand side can be factored as y minus 1, y minus 2. And so we have this product of factors equaling 0, which tells us that our two solutions here will be y equal 1 and y equal 2. So here we have two different y values for different solutions. Once we have solved for one of the variables, like y here, we can go back and substitute them into any of our equations to find x. Recall that we actually know that x is y minus 1, and so we can use that to find x for each. So if y is equal to 1, we get x is 1 minus 1, which is 0. And so we get the point 0, 1. And if y is equal to 2, we get x equals 2 minus 1, which is 1. And so we get the point 1, 2. And so here we see we have two solutions, 0, 1 and 1, 2. So this particular system has exactly two solutions. Before looking at a different example, let's look at an alternative way we could have solved this equation by using elimination. Notice that in this particular equation, the left-hand sides include x minus y and y. And so if we simply add the equations together, the negative y and y will cancel. And so by adding our two equations together, the left side will be x minus y plus y, which will be x, and the right side will be negative 1 plus x squared plus 1, which will be x squared. We can now solve this equation. We can subtract x to the right side, so we have x squared minus x. We can factor that right side to have x times x minus 1. And since this product is equal to 0, we see that we have two possible values for x, 0 and 1. We can now go back to substitute these into one of the original equations and see that when x is 0, y is going to be 1, and when x is 1, y will be 2. And therefore, we obtained the exact same solutions that we did previously, 0, 1, and 1, 2. So as this strategy shows, this particular example can be solved using substitution or elimination. This is sometimes the case for systems of nonlinear equations, but sometimes there are cases where only one of the approaches will yield a usable solution. For our second example, let's consider the system x squared plus y squared equals 5 and 3x minus y equals 5. Note that the first equation is not linear. In this case, it's actually a circle, while the second equation, 3x minus y equals 5, is a linear equation. The first thing to observe is that there's really no way of using elimination to solve this problem. The first equation involves only x squared and y squared, and the second equation only involves x and y. And we're only allowed to multiply by constants, not by variables. And so there's no way to multiply these two equations by numbers to get two of the coefficients of a variable being negative of each other. And so the really only way we can solve this particular system is using a substitution. So in this case, the easiest variable to solve for would be the y in the second equation. And so if we go to solve for that, we see that negative y would be negative 3x plus 5. And therefore y would be positive 3x minus 5 by changing the sign on both sides of our equation. And so we're going to substitute y equals 3x minus 5 into our first equation. When we do that, we obtain x squared plus 3x minus 5 quantity squared is going to equal 5. And now we're going to expand out the squared term and simplify. So we have x squared plus 3x quantity squared will be 9x squared. When we expand that out, we're going to have 3x times negative 5, which is minus 15x. But then we have to double that, so we're going to have minus 30x. And then plus 5 squared, which is 25. And all of that will equal 5. We're now going to solve this quadratic equation by simplifying. So we have x squared plus 9x squared is 10x squared minus 30x. And subtracting 5 from both sides yields plus 20 equal to 0. At this point, we notice all the numbers on the left-hand side of our equation, all those coefficients are divisible by 10. And so we can multiply both sides of this equation by 1/10, or alternatively divide by 10. And we have x squared minus 3x plus 2 equal to 0. We can factor this. This factors as x minus 1, x minus 2. And so we get solutions of x equal 1 and x equal 2. We now take each of these values of x and substitute them into the equation for y, which was y equals 3x minus 5. And so when x is equal to 1, we get y equals 3 times 1 minus 5, which is y equal negative 2. And when x is 2, we get y equals 3 times 2 minus 5, which is y equal 1. And so here we end up with two solutions again. We end up with the point 1, negative 2, and the point 2, 1. So these are our two solutions to this particular system. In this example, we consider the system x squared plus y squared equals 26 and 3x squared plus 25y squared equals 100. Notice that in this case, both of our equations are nonlinear, and therefore substitution is going to be very difficult to do. And so here we really have no choice but to try to adapt the elimination method to this particular system. Notice that here both equations have an x squared and a y squared, and so what we can try to do is eliminate one of those variables squared, either x squared or y squared. And we can do either. In this example, we'll eliminate the x squared. The easiest way to do this would be to multiply the first equation by negative 3. And so we'll end up with negative 3x squared minus 3y squared equals 26 times negative 3, which will be negative 78. And then we'll just leave the second equation alone because now the x squareds have opposite coefficients, and therefore will be eliminated when we add these two equations together. All right, so the negative 3x squared plus 3x squared will become 0. We have negative 3y squared plus 25y squared, which will yield 22y squared. And we have negative 78 plus 100, which will yield 22. And so this equation results in 22y squared equals 22. Dividing by 22 gives y squared equals 1. And then to solve for y, we have to take the square root of both sides. And the important thing to remember is that when we do this, we do need to include a plus or minus symbol. And so we have y is plus or minus square root 1, which is better known as plus or minus 1. This plus or minus symbol cannot be forgotten here because we do have two different values of y whose square is going to be 1. And this will generally be true in a system like this when we're using the variables squared. So now that we have our two possible values for y, we can substitute each of them separately into one of the equations, one of our original equations, and solve for x. So we'll use the first equation here since it's a little bit simpler. And so if I let y equal to 1, we're going to get x squared plus 1 squared is equal to 26. 1 squared, of course, is 1, which we can subtract, and we get x squared equals 25. And taking the square root of both sides here, we get x is plus or minus 5. Again, it's important to make sure we get both of our solutions, x is positive 5 and x is negative 5 here. And so it turns out that this particular solution will give us two different solutions corresponding to y equal 1. We'll have the solution 5, 1, and the solution negative 5, 1. We also need to look at what happens when y is negative 1. That's our other possibility for y. And so here we have x squared plus negative 1 squared will equal 26. Negative 1 squared is positive 1, so this will just be x squared plus 1 equals 26. And like before, we obtain x squared equals 25, and x will be plus or minus 5. And like in the first case, this gives us two possible solutions. We get the point 5, negative 1, and the point negative 5, 1. Negative 5, negative 1, sorry, again. So we end up with these four solutions to this particular system. 5, 1, negative 5, 1, 5, negative 1, and negative 5, negative 1.